Alright, this is video 2 of a three-part series about applications of derivatives and kind of the key ideas that relate to them. This one is about implicit differentiation, which is kind of just regular derivatives but on steroids, and it incorporates the chain rule into it as well. So let's take a quick peek. We're going to try and relate this back to regular functions as much as possible. Something that I love about this video in particular is that there's tons and tons of cool pictures that you get to see along the way when things aren't differentiable in the way that we would expect. Implicit differentiation kind of lets us do some cool things. So far we've worked with really friendly functions, and you'll see down here in the corner I've added a picture of every function that we've got along the way. The only reason I wouldn't include it is because if it was distracting. So far we've worked with this friendly function, and they've already been solved for y. So the y value equals stuff, but it could be very easy that we didn't have that. So if we took the derivative of this, it's quite simple. All we would do is take the derivative of the first thing, so we would do d dx of y, and then we'd take d dx of negative 3x squared, and then d dx of 5, and we just take the derivative of each piece because that's what the sum and difference rule says, and then we get dy dx equals, negative 6x is the derivative of that, plus 0, and so our function is really friendly in that way. But what happens when we take a derivative of a function that looks like this? This is really complicated. It's not solved for y yet, but hopefully you can see that x times y equals 1 is easily solvable for y. If I just divide by x on both sides, I see that y equals 1 over x, which is a function that we can start to work with. I can think about this as x to the negative 1, and dy dx is going to be negative 1 x to the negative 2, and this is easily differentiable. But let's take a spin on it. Let's assume that we can't do that, that we can only take a derivative of it as a product rule. So we would need to think of this as x times y equals 1, and if I took the derivative of this, we would be doing d over dx of this and d over dx of this. Well, we know the right side is going to be 0, but the left side is now a product rule. It's the first times the derivative of the second plus the second times the derivative of the first. So let's think about it in that way. The first being d over d, being the x part. So the first times the derivative of the second, plus the second, or y, times the derivative of the first, d over dx of x. Well, we know that, x times dy dx plus y times dx. Well, what's dx? Dx over dx, the change in x changes as the x changes. Well, this is just a funny version of 1. So that is just 1, and the derivative of x is 1, and we've known that for a long time. So we're left with this kind of funky solution of x dy dx, and it's multiplied, plus y equals 0. And if I solve this, I'm solving it for dy dx. X dy dx, I subtract y equals negative y, and then divide by x. Divide both sides by x to get this. So dy dx equals negative y over x. Well, that's funky. This isn't what I expected to see here, because when I did it derivative the proper way the last time, that's not what I got when I took the derivative. Dy dx these don't look the same. Well, the nice thing is that I already can solve for y. So I know what y is. Y is 1 over x. So let's just substitute that in here. And I'll show you what that looks like. So if I substitute it in here, and I'll try and make it so that you can see it. So dy dx equals negative. The y value is 1 over x, and then I'll just copy everything else, all over x. Well, this is a fraction on top of a fraction, and that's the same as negative 1 over x times, keep it, change it, flip it, 1 over x, which is negative 1 over x squared, which is what we have here, negative 1 over x squared. So we actually do have the same thing in both situations, just one is more complicated than the other. So just take a look at this. If you need to pause the screen and review what we did over here, that might not be a bad idea. But we're going to do a little bit more. This is the logic behind it, and so I want to start there, and then we'll go into the procedure of how to do it quickly. So for problems like this, we're a lot less lucky because we're not able to solve for y in this problem. And I hope you see down here, this doesn't even appear to be a function in our regular thinkings of how functions work, because it fails the vertical line test. So when I can't solve something like this, I need to approach it in a slightly different way. We need a technique that helps us solve this, and we're going to return to this problem actually. I don't want to start here. I want to come back to it in just a minute. So before we do the problem that we did, we're going to go back to the very first example. I could have taken my first example and rewritten in a slightly different way. If I were to add, 3x squared to both sides, I could have rewritten it as y plus 3x squared equals 5. And then the derivative would be dy dx. If I take the derivative of the first thing, d dx of y, and d dx of 3x squared, and then d dx of 5. Sorry, my d's are not turning out the way. So d dx of y is dy dx. The derivative of 3x squared with respect to x is going to be 6x squared, so 6x squared. And then the derivative of 5 is, well, 5. And for us, this is super nice because all I have to do is solve for dy dx, and I get what I got before. Dy dx equals negative 6x squared plus 5. And if you go to the beginning of the video, you'll see that we got the same result no matter how I solved it, whether it was one way or another. So this is an important piece, is being able to manipulate it so that I don't have to take only the derivative of one side. I can kind of do both sides, take the derivative at once. But when we encounter a problem like this, they become a lot more complicated. Again, notice that I cannot solve for y in the traditional way that I would want to. If I take the square root of both sides, I actually run into two problems, which is y there as it would give me the top part of the function, and we're getting the negative part of the function. And notice this is, again, not a function that is differentiable in an easy, straightforward way. So what I want to do is that I want to take the derivative of y squared, the derivative of x plus 4, and the derivative of the left side, the derivative of x plus 4, is just 1 because 4 goes away, the derivative of x is just 1. But y squared becomes a little bit more complicated. And in fact, I want to use the chain rule to do the derivative of this left side. So the derivative of y times y is the first times the derivative of the second. So the first times the derivative of the second plus the second, which is just y again, times the derivative of the first, which is just dy dx again. And notice that if I combine like terms, these are exactly the same thing. It's going to be 2y dy dx, which is essentially the same as doing the power rule and multiplying by the derivative, by the chain rule, because we don't know what y is with respect to x. So we have to use the chain rule. So we have to eventually take the derivative of y with respect to x. So if I look at this, then the derivative of y times y is 2y dy dx equals 1. Well, boy, I'm in a pickle here because I need to get the dy dx all by itself because that's what I'm looking for. I'm looking for the change in y with respect to x. but it's just a big multiplication problem, 2y times dy dx. And all I would need to do is divide by 2y on both sides. So it cancels out, and I'm left with dy dx on the left side and 1 over 2y on the left side. And it's as simple as that. This time, our derivative has y's involved in it. So this is going to get more and more straightforward as we go. We're going to go over one more kind of understanding piece before we do a few more examples. So implicit differentiation is just the chain rule, but it's in general. When we take the derivative of y, it's just the chain rule because we don't know what y is with respect to x. So if I take the derivative with respect to x, notice that the thing that we're taking the derivative of is x, and since there's no x's, y is a function of x. We have to say, hey, we gotta do the chain rule here. So the derivative of y squared is going to be 2y times the chain rule, because I don't know what the derivative of y is, dy dx. I'm done. Again, d over dx, the derivative with respect to x of y cubed is going to be 3y squared, and then times the derivative of y because I don't know what y is. And again, y to the power of 4, 4y cubed times the chain rule, dy dx. So I hope that you can see that taking a derivative of a y isn't as scary as it might have looked at first. And we're going to do a few different examples of this. So here we are coming back to the original problem that we were doing before that looked kind of funky, and you can see we still have the same picture here. I just copied the slide. But we're going to do this as an example. So I'm going to take the derivative of each piece separately. I'm going to try and show it as much as I can. So I'm going to do d dx of x squared minus d dx of 2y cubed plus d dx of 4y, and then take the derivative of the right side, d dx of 2. And then I'm going to go through just as I would in any other problem. The derivative of this thing in the parentheses with respect to x is 2x, and then subtract. The derivative of the thing inside, just the chain rule's got to get applied anytime you take a derivative of y. So 2 times 3 y squared times the derivative. The derivative of 4y is just going to be 4y, but I got to take the derivative of y, so 4 dy dx, and then the derivative of 2 is just 0. And when we get to this stage, I'm looking for the derivative dy dx. That's what I'm solving for. I'm looking for dy dx, and I'm almost there. I'll just need to do quite a bit of algebra to get there. If I subtract 2x from both sides, I get negative 6y squared dy dx, and I get 4 dy dx equals negative 2x. And I just wanted to show this to you because now I can actually factor out this y. I always got stuck here, and it's as simple as just factoring out a dy dx. So my dy dx is in front, and everything else is left behind. Equals negative 2x. And so when I start solving this, all I'm solving for is dy dx. I just will divide, because it's a big multiplication problem. I'll divide both sides by 6y squared plus 4. Divide both sides by negative 6y squared plus 4. This stuff cancels out this stuff because it's a big multiplication problem. I'm left with dy dx, and then my answer is negative 2x divided by negative 6y squared plus 4. And so they look really bizarre, but all I've done is use the chain rule on y because I need to. A quick observation is that we've got two different notations. Leibniz, or Leibniz as people call it, Leibniz used this green notation, dy dx, and Lagrange used the prime symbol. And so in the past few problems, we've been using the Leibniz notation, and for the next one, we're gonna start using the Lagrange notation just to show you how you might see it in different ways. And you can pick and choose whichever you prefer. I personally like the Lagrange notation because it's a lot less writing than the Leibniz notation. So take your pick. A couple more problems. We're going to find the derivative with respect to x. And I'm not going to do all the notation. If I take the derivative of each piece, I need to change to a color. 3 y squared times the derivative of y, or y prime. 2, so plus 2y times the derivative of y. Minus 5, minus 5, because the derivative of that, well, I still need to take the derivative y prime. So it's still times y prime, and then minus 2x, and then the derivative of negative 4 is 0. So you'll notice that instead of doing dy dx, I chose to use y prime, and I think that it's a lot easier, at least for me. When I go to solve this, I'm solving for my y prime, and so I'm just doing algebra at this point. So I'm going to factor out the y prime piece of it while I'm at it, and then I get 2x. So factoring out the y prime, I get 3y squared plus 2y minus 5. And then my last step is to solve for y. It's just a big multiplication problem, so I'm going to divide by the stuff. Oh, hang on. That's just not enough space for me here. I'm going to divide by the stuff that I need to get rid of it. 3y squared plus 2y minus 5. Divide by 3y squared plus 2y minus 5. And this cancels this out. And y prime is 2x over this 3y squared plus 2y minus 5. This is actually probably one of my favorite functions. It looks like a puzzle piece. And notice the derivative isn't super difficult to get. I've just been using the power rule and the chain rule and then doing a lot of algebra. Okay, we've got a few more practice problems that I want to show you or have you work through with Taylor. We're just going to kind of do a few extra problems. Notice that this is the equation for an ellipse. X squared plus y squared equals 4 would be a circle, but that 4 makes it an ellipse, and it has a spread. It's kind of squished. It's a squished circle, if you will. And everything is the same. I'm going to do it in blue for everything and do all of my chain rules in red. So the derivative of x squared with respect to x is 2x. The 4 comes along for the ride, 2y. And then I have to use the chain rule, times y prime. And the derivative of 4 is 0. All I'm doing is now solving for the y prime. I'm going to subtract 2x from both sides. So I've got 8y prime equals negative 2x. And all I'm going to do is divide by 8y. Divide by 8y. Those cancel out. Y prime is equal to negative 2x over 8y. It gets easier and easier as you practice more and more. This is also a very fun looking function, and this is probably one of the more complicated ones that we're going to do today. It's going to require the chain rule and the product rule and the chain rule as a piece of implicit differentiation. So this is a really meaty problem. So take your time and don't get frustrated if it seems super challenging at first. Just you'll be okay. So I see that there's a u inside, and so I'm going to need to use the chain rule for that. So I think 3 times 2 of the stuff, x squared plus y squared to the power of 1, because that's the power of 1, because that's just the derivative of the outside guy, times the derivative, and I'm going to just show it as best I can, x squared plus y squared. This is just pure and simple the chain rule. And then I'm going to take the derivative of the right side equals 100. The 100 sticks around for a while. And it's the first times the derivative of the second plus the second times the derivative of the first. So 100 times the first times the derivative of the second. And I'll just use the y prime notation actually. First times the derivative of the second plus the second times the derivative of the first, which is just 1. Man, this is really, really a meaty problem to deal with. And the only derivative that we still need to take is this blue stuff. So I'm just going to kind of clean everything else up. So it's going to be 6 x squared plus y squared times, the derivative of this is just kind of piece by piece, times 2x plus 2y, implicit differentiation, y prime, and then everything else is going to come along for the right. I'm actually going to go ahead and distribute this back into these guys just for now, because we're going to need to do some solving in a minute. So I see 100 x y prime plus 100 y, and notice the difference between y primes. I'm actually going to go through and highlight them in yellow, all of my y primes. I only have 2, which is handy. Oh, and that didn't look super duper nice. I wish that it was nicer. Y prime. So you could see it. So I've got my y primes highlighted. This is just a kind of a mess, if you will, in that I have to solve for y eventually, and I'm not looking forward to it. It's a lot at this point. The calculus is done. This is all algebra. I'm gonna kind of speed through it here real quick, and I'll show you when I get to the other side. So you can see I kind of rushed through this, and I wanted to show you that all I did was distribute this first piece. I did all my distribution, and now I just distributed the 6, and I'm subtracting everything that doesn't include a y prime from the left side. So I'm taking away this because it doesn't have a y prime. I'm taking away this because it doesn't have a y prime. And eventually I'm going to move the y prime from over here back over here. I just need a little bit of extra space. And I went ahead and moved the 100y over. I just subtracted 100xy prime to here. And hopefully you see all of the y primes again. I'm going to factor out the y primes, and I'm going to divide by all of this stuff, and I'll show you the answer in just a moment, but I need a little bit more space, so hopefully get some more space up in here. There we go. And just like that, we've solved for y prime. And part of what I love about y prime notation, the Lagrange notation as opposed to the Leibniz notation, is that I can do y prime much faster than I can do dy dx, and it saves me a lot of space, especially when there's this much algebra. I just want to take a note and notice that the calculus actually stopped right here, and everything below here, all of this is just solving using algebra and pre-calculus skills. So it's not too much. This is a big problem. Thanks for hanging in there. Take a moment to review this or pause the video to just see the whole process as it worked. I only skipped one step, and that was moving this 100 from over here, this 100 xy prime. I subtracted it from both sides, and I moved it over here. So that's the only algebra that I skipped. One more problem, then we're done. All right. This is a sine function, and so implicit differentiation also works for trigonometric functions. All it really is if I'm taking the derivative of a function with respect to y. It's just the chain rule disguised as a non-chain rule function. So the derivative of sine y is cosine of y times the derivative of the inside, which is dy dx, and the derivative of x is 1. And so if I take the derivative of both sides, then I can solve by dividing by cosine of y, and my derivative dy dx is 1 over cosine of y. All right, this process is essentially the same every time. You always have to use the chain rule when you're taking a derivative of y. The derivative of x is the same as it's always been. When you take the derivative, then you solve for your dy dx, or if you want to use y prime, you can use that notation too. This always works until higher maths, when it starts becoming more interesting. Thank you for watching the video. Take some time, again, look up some practice problems or do some from our book to practice the ideas of implicit differentiation. When you practice, it'll get faster and easier. You'll be really glad you did. Thanks for spending the time and watching.